Okay, so we're going to learn our first algorithm today. What is this algorithm called? I'm here to predict marks based on the hours. Okay, so this is the hours that student studies, and this is the marks that they have obtained. So the situation is like this: you want to predict how much marks your cousin would get. Okay, your cousin is appearing for 10th class board exam, and you want to predict the marks he or she is going to get. So what you do, you go to your cousin's senior. That's called supervised learning because you have the data. You'll go to your cousin's senior and ask them these questions. How many hours you studied and how much marks you got. Okay. Now here you only have one column based on which we are predicting. Okay. So this is hours column. So that's only one column, and assumption is that only one column impacts, let's say, marks, number of hours you study. That's it. Okay, no other factors impact marks. So we'll go and you ask the senior, and this is the data that you get. You talk to how many rows we have? We have 30 rows. So you spoke to 30 people, 30 seniors, and got their number of hours they studied and the marks they obtained. So based on this, you want to predict for your cousin, right? So now once you get the relationship, if you find the relationship between hours and marks, then you replace your cousin's number of hours here and you will get the corresponding mark, right? As simple. That's what regression does. Okay. So we are going to do this. This is the data set. I'm going to click on the raw version of it. Okay, so this is the CSV file. Copy this path. And now we'll go back to our PyCharm. And I'll replace this link with the data set link. Okay, great. Now, what is the concept here? Okay, the concept, okay, the regression concept or the first algorithm I'm going to do here, let me put it here. Okay, regression. Why? Because we have past data and we're going to predict numerical continuous value, right? Output would be a continuous value. Output, which is marks, is a continuous, okay, continuous variable, right? So we're going to use regression algorithm. The first algorithm that we're going to talk about is called simple linear regression. Algorithm is simple linear regression. Now, okay, look at these names. Why do we say simple linear regression? Simple because it has only one x. Only one x column. What is x? X is your dependent variable. Dependent variable. What is dependent variable? The variable that will impact your outcome. So here, x is impacting your outcome. Y will always be 1, right? Y will always be 1. Okay. Now, this is called regression, of course, because it's going to give us output as numeric value. And why linear? Because we are going to have a linear approach. Okay. Assuming that data set is linear. Okay. So, okay. And how to know it is linear, I'm going to show you in some time. Okay. We'll draw a scatter plot and we'll see. Okay. So this is called simple linear regression. Okay. Now, when you talk about variables, okay, we have something called as univariate. Univariate is one column. So your data set has just one column. Your data set has just one column. That's all. No other thing. Okay. Just one variable, one column. We're not talking about X or Y. We're talking about the data set, whole data set. You have only marks, let's say, or you have only hours, let's say, or you have only gender, or you have only age. That's called univariate. Okay. data set. Univariate data set. Data set which has only one variable. One variable means one column. Okay. And there are some some analysis that we can do on one column. What are the analysis that we can do on one column? Again, it depends upon whether you have categorical data or you have numeric data. When you have numeric data, you can draw a line graph, you can draw a bar graph, you can draw a histogram, right? Again, we'll talk about this when we get into the the graph part of it or plotting part of it. Okay, you have a gender, you can create a bar graph, you can compare like how many male, how many female, right? Now, when your data set has two columns, the data set that we are working today has two columns. Okay, we call them as bivariate. Bivariate, univariate, one, right? Uni is one, right? So univariate, bivariate. Bivariate means two data set, two columns, two variables. Okay, but of course, when you are doing machine learning, you need to have at least two variables, right? One will be X, one will be Y. Otherwise, you can't perform analysis with one variate, right? So, you have bivariate, and more than two, we call them multivariate. Okay, more than two columns, we tell them multivariate. So here you have simple because you have only one X, one is it dependent variable? No, X is not
X
called
is
dependent variable. Y is dependent because Y has to be predicted based on X, isn't it? So Y should be called as dependent variable. This is your independent variable. Okay. Okay. Y is dependent. If Y is independent, then you can't predict. Okay. If there's a variable which you cannot influence anyway, then you can't predict, right? That's beyond your control. But what we are saying is, okay, Y is not beyond our control. So Y is dependent on X, and X is independent. Okay, so X can be anything, but Y cannot be anything. Okay, number of hours you study, it's up to you, right? You can do anything. You can choose not to study. You can choose to study 10 hours a day. It's up to you. Okay, but marks is not like that. Marks, okay, if you study well, even though you don't want good marks, you'll get good marks, right? So Y is your dependent variable. So X is independent variable, Y is dependent variable, and here we can have multiple variables, right? But since it is simple, we're only dealing with one variable here. So X is your independent variable which influences Y. Okay. Now, okay. So how does we know that it influences Y? Okay, can we figure out? Okay, so let's first figure out if Y is really dependent on X or not. Okay, now let's look at this example here. Okay, we have only two columns, right? So X will be 0 to 1
1.
in this case, right? Because X is only one. Previous example, we had 4. So we said first 3 is X and last one is Y. And here I can say -1, right? -1 is single column Y. Okay. Now in this case, there are no missing values. Okay, there are no categorical values. Okay, so we don't have to perform this thing. Okay, we don't have to perform column transform also.
Yes.
But we need to divide into train, test, and train and test sets, because that's how we discussed that, for every algorithm we have to do it. Now here, since we have only one X, there is no need to perform scaling as well. Okay, it's only scaling is performed when you have two different columns and they have values in different range. That's when we perform scaling, right? But here scaling is not required. Okay, but before we get start doing our analysis, okay, we need to check if this data really are dependent on the Y is dependent on X or not. So we call this as EDA. EDA is, what is the full form? Remember the 7 steps that we did?
Exploratory data analysis.
Yes. Okay. We need to do, okay, exploratory analysis to make sure that we understand the data. Okay. So here, okay, I'm going to simply do, are we using PLT here? No, right? So, okay. So let's say I go and say import matplotlib.pyplot as PLT. Okay. Now, matplotlib is a basic library for drawing any plot. Okay. So again, we will see later how to draw Seaborn plots. Okay, but matplotlib is basic. Matplotlib is basic. Okay, even Seaborn is based on this. Okay, so import matplotlib.pyplot. This has all the plots. Okay, it has scatter plot, it has line graph, bar graph, okay, multiple heat map, all those things. So we will also learn to draw these plots. Okay, so which plot do you think will be useful here in this case? I want to study if X and Y are related. Does X influences Y? If X influences Y, only then it makes sense to perform, move ahead. If it doesn't, then doesn't make sense
Yes.
to move ahead, right?
Yes.
Okay. So we will draw a scatter plot. What is scatter plot? Scatter plot is XY, so it's a dot plot. Okay, you have dots there. And each dot represents your XY value. Okay, so let me show you how. So we have used plt.pyplot. So plt has function called as scatter. Okay, scatter. Now here you give X value. Okay, and okay, then you give Y value. Okay, what is X? I just put one just for placeholder. We'll go and replace this. Now on X-axis, which column should we put? Which column do you think will be better to put on X-axis? X.
X.
Okay. Okay. X is something that we already know. The X will always have independent variable, and Y is what is a dependent, right?
Dependent.
So we'll say X equal to X and Y equal to Y. Okay. Now Y is fine. Okay. But the problem with X is a multiple format here. It can have a multiple column, but X-axis will have only one value, isn't it? Okay. So the best thing is that here you have to give the column names. Why? Because see, X can have multiple. The way it is written, it says from 0 till, right? It can have multiple columns. The way it is defined is multiple columns. But you can't have multiple values. X will have only one because it's a two-dimensional graph. Okay. Now, if we had multivariate, we could have created multiple scatter plot, or we have something called as pair plot, which we'll see. Okay. Could draw pair plot or multiple scatter plot. Okay. Pair plot is also multiple scatter plot only. So, okay, we'll do that when we do multiple linear regression. That's the next topic, and we'll see that. So here's scatter plot. I'll say X of, okay, the column name. And what's the column name here? Okay, let me go back to this. It's called R's, right? I'll pick it from the data set. So it is R's. Okay. Now, I have to use something called as plt.show. When you are doing this in any editor, whether you're working with PyCharm or say VS Code or any editor, you have to give plt.show. You have to specifically mention, show me the plot. Okay. But if you're working with notebooks like Colab or Jupyter or any of these notebooks, then you don't have to write this. Okay. Jupyter or Colab, all these notebooks will automatically display the plot here, plot in when you run it. But in editors, you have to write this. Okay. So yeah, and if you write it, there's no harm, but your editors will not work or will not show the plot if you don't write plt.show. So let me run it. Okay. And okay. So see here, index. Only integers, slices, ellipse, okay, are valid index here. So here also what I'll do, okay, I will say y of, okay, or rather directly let's use data set. Okay, you can do this even before you perform xy, right? We'll just want to make sure whether you have the right data set or not, right? Now let's run it again. Okay, you may not be able to see because I need to share my entire screen. Am I sharing entire screen? Yeah. You see this?
Yes.
Now, what did we put on x-axis? We put hours on x-axis, right?
Yes.
And on y-axis, we put marks. Now, if you see, this is what we are getting. By looking at this data set, we know that there is definitely some relationship between x and y. Okay? So,
Yes.
scatter plot, okay, is xy, shows xy relationship, right? Shows relationship between x and y variables, right? And you can have, okay, you can have what is called as positive correlation. You can have negative correlation, and you can have no correlation. Okay. Now, what we saw, okay, was kind of positive correlation, right? Because x was impacting y. Okay. Let's go here. And if I put correlation, okay, okay, I will turn image. Okay. Now, can you look at this image?
Yes.
So this is what we saw, right? Our dots were, okay, increasing as you increase y, or as you increase x, okay, because x is independent, right? So we should always start talking from x perspective. So as you increase x, y also increases, right? So this is
Mm.
called positive correlation. Okay, I'll talk about what strong is. So hold on for that. Positive means as you increase x, what is called directly proportional. This is what we'll have learned in school. Directly proportional. Directly proportion means what? Okay, relation is x directly proportional to y, right? Same concept. Okay, inversely proportional means we say 1 by x. I mean x directly
Yes.
proportional to
Yes.
1 by y,
Something is
reverse,
on.
right?
Yes.
So positive means as you increase x, your y also increases. That means as you study more number of hours, your marks also increases. Okay, so if dots are in increasing order, we say it is positive correlation. Negative correlation is if dots are in decreasing order here. So as you increase x, y comes down. So maybe you
Yes.
can replace number of hours you study with, let's say, number of hours you watch Facebook. So as the number of hours increases, your marks will come down. Then we say number of hours you spend on Facebook is inversely proportional or negative correlation. Inversely proportional is negative correlation. So we say it is negative correlation with respect to x-axis or x variable. In our case, we got positive correlation. No correlation is when dots are everywhere. So you see here, value is x is low, you have a high y. If x is low, you have a low x also. So here also it is positive. So everywhere dots are almost everywhere. You can't find a trend here. If you can't find a trend, that means there is no correlation. And if there is no correlation, then your analysis will not be effective. If there's no correlation, then no point of doing, because x does not impact y. If x does not impact y, no point in spending time and effort trying to predict y from x, because x does not influence it. Okay, so it is important to know whether it is a positive correlation or negative correlation or no correlation. So, okay. So first thing is, okay, now let's say there's a strong, I mean, there's a positive correlation. Okay, we'll go back to our example. So we know there's a positive correlation. Now, if it is positive correlation, then what is the value? Okay, what is the value? So correlation value, okay, correlation value changes from 0 to 1 here. Okay. And in negative correlation, also it changes from 0 to -1. Okay. That's the correlation. So in fact, I don't have to mention it along with positive. Let's do it here. Correlation can change from 0 to +1 or -1. I'll say plus or minus. Plus or -1. Okay. This tells you how much is the correlation. Generally, okay, 0 indicate no correlation. Okay. And it is very difficult that there will not be any correlation. So in our analysis, what we say is, if the correlation value is between 0 to plus or minus. See, minus or plus only indicates whether it's going in positive direction or negative direction. So when you see negative, it is negative correlation. And when you see positive, it is positive correlation. But the magnitude tells you how strong is the correlation. How strong is the correlation? So if the correlation value ranges from 0 to plus or minus 0.5, we say no correlation. Okay, we ignore the correlation. Okay, even 0.5 we ignore. Okay, now if it is between 0.5 and 1, we say correlation. Now again, if it is very close to 1, we say strong. If the correlation value is closer to 1, we say strong. Okay, strong correlation. And when I say strong, it can be both positive or negative, right? Strong correlation values is, will be closer to plus or -1, right? As your values are closer to 1, and magnitude 1 I'm talking about, it is stronger. Plus means positive correlation, negative means negative correlation. Now, when we go back to the same diagram here, you see dots are almost close to this line. What is this line called? This line is called a regression line. Okay, and this is what we are doing, right? This line is called regression. What is regression line? So regression line is a line, straight line, of course, and that's why we say linear, okay? And we will see that line may not be straight line, okay? So in linear regression, we expect this line to be straight line. But as I said, line need not be straight line. It can be a figure. It can be a, hyperbola, it can be a circle, it can be any geometric figure. Okay, we need to figure out what is this figure. That's it. Okay, but let's say, okay, it is straight line. So regression is a straight line here. Okay, which is also called as best fit line or line. Okay, which can represent entire points, entire dots. So line that can represent entire dot. Now, in this case, it is possible to draw infinite lines, isn't it? Then why only this line? You can have infinite lines, right? So if I take this picture and go to paint, let's say. Now you can say that we can draw a line from here also. Sorry, that's not line. We can draw a line like this also. We can draw a line like this also. Okay, the color matches. Let's use different color. We can draw a line like this also. Why not yellow line? Why not red line? Why only this purple line? Okay, this is called best fit line. The best fit line means if you take the error, and what is error in this case? Error is the distance between line and the dot. Okay, line and the dot. Now, these are the dot, and you see almost all the dots lie on the line. So if you add them all together, all these dots together, the total error, what you get, would be very close to 0, right? So when dots are closer to, so, okay, forget about weak and other things. Now, this line, if you take yellow, red, and purple, okay, now if I try to measure the distance between yellow line to the point here, So this is the distance, right? This is the distance. This is the distance. This is the distance. Now, if I try to measure from point to the red line, this is the distance. Okay, this is the distance. And then I try to measure the distance between purple line and the dots. Which line will have the minimum error? Purple line,
Purple.
right? If you add them all together, if you add all the errors together, purple line will have the. So here we have infinite lines. We draw and check which line has minimum error with the given points. That is called as best fit line, or also called as regression line. And that line represents the entire point. Okay. So of course you can have multiple lines, but the line which will have the minimum. So if I try to deviate little bit up or down, the error increases. Okay. So in this case, we are saying that this line represents the dot. Okay. Now if the dots are farther away from the line, like in this case, error is more, we say weak correlation. If the dots are closer to the line, we say strong correlation, right? Now it can be weak in case of this also, negative also, it can be weak in case of positive also. Okay, so weak indicates like distance above 0.5 but away from 0.1. So generally, 0.5 to 0.7, we say weak correlation, 0.7 to 0.8. It's up to you, okay? There is no hard and fast rule. Moderate means, the error is less than weak but more than strong. So moderate, we'd say 0.758, more than 0.85, we say strong. Okay. Now, what is the importance of correlation? Importance of correlation is higher the correlation, more confident you will be about your data set. Error will be less when you're making prediction. Okay. Error will be less when you're making the prediction. First of all, why do we say it is regression line? Okay. Why do we say it is regression line? No, okay. Now, generally, okay, and when you are dealing with these data, okay, and when you are dealing with such problems, and let's say you have no idea about regression, okay, you don't know what regression is. In such cases, what we generally do is we take the average, right? Now, let's say if you want to predict your cousin's marks, same problem objective that we started with today, you want to make some prediction, right? So what you do, you go to the class and you see, okay, what was the average marks obtained by those students in the previous class, the same school? Oh, it was 75. You'll say, okay, my cousin will get about 75. Now, since I do not have capability to measure the very specific, very personalized performance of my cousin, I'm taking average of the class only. Correct? That's what we do when we don't know regression. Okay. So in case of no relation, okay, here, that probably works. Okay. You draw a average, you take the average of this, and average is like this. So you say this is the average value for this class. Okay. But on average, okay, you see, it's not getting influenced by specific quality of that data point. Regression comes into picture, okay, because we're saying, okay, not all points are average in all cases. Okay, we should not take average. Okay, now if you take this case only, if I start taking average will be somewhere here. Now, average somewhere here. Now, this works well. Looking at the data set, if you see, this works well for points which are around this point. Okay, you can say, but here you see, these values have higher values and these have lower values than the average. So I cannot put all these values as in same boat or the same situation as these values. So here clearly average line is not the perfect way to predict these values. I need to come up with something different. That's why regression. Okay. Why it's called regression? Why not progression? I say regression. Why not progression? Okay. Now, again, I told you most of these algorithms were based or used by biologists. Okay. And regression is something which is being used for more than 100 years. Okay, it was developed in 1818 only. Okay, so it's not something new. It's not something that we have developed in last 5 years or 10 years or 20 years or 50 years. Okay, it's very, very old technique. So now see, why are we studying as part of data science now is that with with access to a lot of data, right? With internet, we can capture a lot of data. We have very powerful computers which can process millions of rows, right? So the study has become more prominent. But scientists were using these concepts even 100 years back. So regression it's called regression because the nature, okay, if you see, or the biology, if you say, biology always brings everything to a level. Okay. So when I say to a level, what it means is, um, okay. So let's say you have, we'll try to understand from cricket perspective. Okay. Now let's say, okay, these are, let's say, position of batting position. Okay. And let's say this is the runs that are scored by the batsman.
We
So
can
general,
make that overs
sorry,
as well, right?
not overs. Okay. We'll
Overs
talk
and
about the
runs,
batsman.
40
Okay.
mind.
No,
Okay.
we'll talk about batsman. See, batsman influences the runs, not the overs, right? If you have, um, who's the, if you put, uh, what, Chahal in the 20th over, can he score runs? No. Okay. See, we have to talk about things which impacts why. I'm talking about runs. Runs is impacted by the batsman. It doesn't matter where Kohli bats, right? Is it over 1 or over 20 or over 50? Doesn't matter, correct? But if I put you, okay, and the first over, okay, obviously at national, international level, you won't be able to score runs. Yes or no? Okay. So if I take overs, okay, if I take overs, now you can take overs and runs, let's say, for example. Okay, we'll talk about what you said. Now, if I take overs and run, okay, it's possible that you will score 0 here. If you send number 10 batsman here, you'll have low runs. Okay. Here also, if you have, okay. So it doesn't matter. Okay. If Kohli or Dhoni is batting here, probably you'll have high runs. Here you'll have high runs. But here, if some number 10 batsman is batting, they'll have low runs. Right? So there's
Yeah.
no correlation between overs and the runs. Okay. The correlation between overs and run is because of the batsman, the quality of batsman that is batting. You agree
Yeah.
with me?
Yeah, but when we see cricket matches, right, they're for complete team. Like if for example, if India has completed their innings,
Okay, so I'll tell you one
you can see
example.
a bar
Okay, I
graph
understood what you're
exactly
saying.
like a scale
You
plot.
know, I
Like
understood what you're saying.
yeah,
So
so
generally, there are some sentiments. Okay, or sentiment
okay,
is, if I don't watch cricket match, India wins, and if I watch, India loses. Some people have that condition,
yeah,
right?
yeah, yeah,
Some
yeah.
people will say, if I wear red dress, India wins. If I wear any other dress, India loses. Right? You see that
Yes,
that happens. Maybe that will happen in 8 times. But do you really think there is a correlation between your red dress and India's
no,
winning?
no, no.
Right? So again, see, when you're talking about correlation, you have to figure out real correlation, not
Okay,
what you assume, what you think. Okay. If I wear this dress, India all wins. Okay, you will wear that dress and India wins. So do you get the credit? Do you become the man of the
no, no,
match?
no.
Right? So the point I'm trying to make is, does that factor really impact? Okay, you might see, okay, higher, lower, as you increase the overs, the run rate increases. Initially run rate might be about 3 runs,
Mhm.
towards it might become
Yes,
10
yes,
runs per
yes, yes.
over.
Yeah, yeah,
Okay,
exactly. Yeah,
so you see that, okay, over is increasing,
yeah.
but it is not over because of the over, it's because of the batsman who's batting.
Yes, yes,
Okay,
yes,
if you
yes.
do not lose wicket, only then your runs is going to be high. If you lose wickets, then you don't get high runs, correct? So it is not because of the, okay, it's not
Okay,
because of the, okay, and again, see, it could be because of both. Okay, and that we'll talk about in multiple linear regression.
okay,
It could be
got
because of batsmen also and overs also.
it.
Now, okay, what we say in multiple linear regression is, you might have multiple X. Let's say this is batsman, this is overs, and this is runs. Now, is there a correlation between these two? Of course, X1 has correlation. Okay. Okay. You have higher order batsmen, your runs are higher. If you
Runs will
have,
be high.
okay, end overs, runs are higher. Okay. So X1 related to Y and X2 is also related to Y. Okay, fine. But between Xn and X2, is there any relationship? Yes, there is relationship. What is the relationship?
Yes.
So X1 and X2 are also related. If X1 and X2 are also related, and X1 is related to Y and X2 is related to Y, then there is no point of using X1 and X2 together.
Exactly.
Okay, because
Okay.
both are influencing Y. Okay, so if both are influencing Y, then
Yeah.
there's no point of
Yes.
taking both. Okay, simple
Correct.
example is if I have to predict number of cards, let's say.
Mm.
Now, if I have to predict number of cars, I also need to predict number of wheels, number of steering wheels, number of nut bolts, etc.
Yeah.
But if I already know, okay, how many cars, I can simply multiply, no? If each car, let's say you pack 5 wheels, okay, 4 wheels plus one extra, right? So if I know if I have to make 1,000 cars, I know it is 1,000 into 5. Okay, so something like that. Because when you have XY relationship, no, if X1 and X2 are also connected, interrelated, then there is no point of taking both together. Because if they are related and one of them is already influencing Y, why do you want to take multiple, okay, variables? Multiple variables will only create complex relation. Complex
Yes.
relation will, one, it will not influence the accuracy, and second, it is going to take more time. Now, if you
More
have to
time.
deal with millions of rows,
Yeah.
it will simply do that. So, point is, what you see always may not be true, right?
Yeah.
So you need to figure out what exactly is causing that relationship. Okay.
Yes. Yes.
Now, so I was talking about, let's say you have batsmen. Okay. So
That's
generally, if you talk about average of batsmen, okay. Now, when you take average of batsmen, average runs, let's say here instead of runs, I take average runs or total runs. Okay, total runs. The position people batting at first, opener position will tend to have higher average
higher
or
averages.
higher,
Total runs.
runs, right?
Mm.
And as you go down, the average runs decreases, right? Their average
Yes.
decreases. Okay. So what you might see is, okay, let me clear this space here. So you might see, okay, um, okay, a relationship like this, right? You might see a
Very clear.
relationship
Yeah.
like this where the average is higher for lower order batsmen, higher order batsmen. As you go to the position, the runs average decreases.
Decreases.
But since this is average, right? You
Mm.
might have somebody, okay, scoring, average, though batting at position 6, they might have runs like this also. Though there may be a batsman batting here, but they might have runs like this also. This is just a regression. This represents entire data so far. Let's say if you have 10,000 players that has played for the country, so this line represents all the 10,000 players. But there could be some player, okay, see, this is the average line, middle line, right? So you have some people above this line and there are some people below this line, right? Not everybody
Yes.
will be on this line. Okay. So, okay. So this line represents the entire data set. Okay. So what it says is, even though you may be a Sachin Tendulkar, okay, scoring at a higher average, but there will be some player batting at position 3 which will score less than Sachin. And most of them will be like this. Only few are exceptional talents. Right? Now, currently you have maybe 100 players playing in Test cricket, right? Not
Mm.
all 100 are great batsmen. You have only 5 or 10 who are exceptional batsmen, right? Other 90 are average only, right? So
Yes.
most of the data set is average. So that's why we say regression. Okay, even though Sunil Gavaskar may be great batsman, but his son was not. His son was below average. So that now if you take average of him and his son, it will be average score only, right? So
Yes.
in biology, okay, generally we say no. If you are tall, your kids will also be tall,
Yes. Yes. Yes.
right? Okay, that's not true. We say that, but biology say that's not true. Why it is not true? Say 1,000 years back, there would have been somebody with 7 feet height or 6 feet height. 1,000 years back. Also, we might have somebody with 6 feet height, correct or not?
Yes, might be.
Yeah, might be, right?
Uh,
So now if you go by that logic that, if you are tall, your kids will also be tall. So this 6 feet kids would have been 6.2 feet, 6.1 feet.
mhm.
Their
Yes.
kid would have been 6.2 feet. Now, after 1,000 years, that
Yes,
generation,
yes,
the
yes.
family, you might see somebody with 10 feet height. Do you see anybody with 10 feet height today?
No.
No. So these things are not true. That's why we say regression. Everything is with, if the average height of Indians is, let's say, 5.9 or 5.8. Let's say if average height of Indians are 5.8. Okay. You might be tall. You might be 6.5. You might be just 5 feet. But your kids, if you are taller, your kids will be closer to 5.8. If you are short also, your kid will be closer to 5.8. Okay, because that's the average height. That's the average regression line that we are doing. Yes, you might have some exception. You might have somebody, so your cousin might be very intelligent. Okay, even, with less number of hours, your cousin studies, they might be able to, or he or she might be able to get more marks. Possible. Okay. Or your kid maybe, may not be that intelligent, and even if they study more number of hours, might get less marks. There are always exceptions, but those exceptions always will come to this regression line or average line. So if average of top 3 batsmen is 55 runs, okay, more likely you will score 55 runs. Okay. If that's not the case, then Kohli would have never scored 0 runs. He would have always scored 50. What it means is, even if he scores zeros, or if he scores 200, okay, in the next match, we still expect him to score about his average only, right? Zero, if he has scored zero, next match, he'll score more than zero. If first match you score 200, next match he's not going to score even 200. Correct or not? Because law of nature is that you have to come to this regression line. Now, this regression line and average line are, the concept is same, just that what we are saying is, no, here, instead of average here, not everyone is same. Okay. These players will score higher, then this will be score little lower, 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 right? So this is, this becomes your regression line, because this X is impacting Y in this way. Now, this is again the average for this group. This is average for this group. So instead of looking at entire thing as one single group, we have divided into 10 groups or 20 groups or 50 groups. And this average is about average of this, one group, average of this group, So we are trying to bring all the values to the regression line. Now, when we run this algorithm, we might get, okay, you might get, let's say, 60 as answer, but it doesn't mean that your cousin will get exactly 60. He or she can get 80 also, can get 50 also. But what we are saying is, it is more likely, very likely, highest chance is that it will score around 60% marks. Right? If so more you're able to capture that factor. Okay. Now, as I said, if your cousin is super intelligent, instead of 60, he or she might get 90 also with same. But are you able to capture that super intelligent thing into your analysis? If you're able to capture the super intelligent thing somehow in your analysis, then again, your answer will not be 60, but your answer will be close to 80, 85. So objective here is to figure out exact parameters that influence Y. If you are able to capture less number of parameters, incorrect parameter will give you everything wrong. But if you're not able to capture all the parameters, you will be somewhere closer to that. Your error will be higher. And this is what we'll see when we do multiple linear. Okay, we'll talk about how to handle or how to see which parameters are important for the final outcome. But here, since we have only one variable, we don't have flexibility, right? So we have to take hours, and that's what we have to predict, right? So did you understand? Okay, the correlation and the regression concept. Regression, okay, is a concept which studies the relationship of X on Y. Okay. And we have to
Yes.
convert that relationship into an equation. Okay. We have to convert that relationship into an equation. And if we are able to convert that equation, okay, then it is easy to predict. Can you tell me what would be the equation here? What could be the equation here? What are we dealing with? We are dealing with what kind of shape are we dealing with here?
Positive correlation.
Shape I'm asking. It's a straight line, isn't it?
Straight
Right? So
line. Okay.
we are talking about straight line. So if it is a straight line, then what is the equation here?
Y is equal to mx plus c.
Y equal to mx plus c.
Yes.
Okay. So that's the equation that we have to deal with, because we're talking about straight line.
Straight line.
Straight line will always have this relationship y equal to mx plus c. Now, what is m? What is c? What is x? We need to know three things, right? And if we know three things, we can predict y value. X
Exactly.
is the value on x-axis, number of
X-axis.
hours your cousin studies. This also you know, right? What we don't know is m and c. So linear regression, simple linear regression will give us the value of m and c. M is called slope and c is called constant. Again, if
Constant.
I go back to this equation here, okay? So if you have drawing this line here, this is called what? C. This is the constant.
Constant.
And this, the angle at which you go, this is your slope.
Slope.
So how do we calculate slope? Slope is delta y by delta x.
dy by dx. Yes.
dy by dx. And what is dy? So if you draw any triangle here, okay? So this is your change in y. So for this particular change in y, this is the change in x, right? So this is your, in this case, your dy by dx or m will be less than 1, right? Because y is smaller than the x, right? X is bigger here. So it will be less than y. In some cases, of course, it can be more than y, more than 1 also. So this is m and x. So ultimately, your simple linear regression is only giving you the value of m and c. Okay, when we run the model will run and give you value of m and c. And then we'll be able to form the equation y equal to mx plus c. Now you change the x and you get corresponding y. So this is the purpose of simple linear regression. Simple linear regression will give us this regression line. Okay, once you get the regression line, then you can easily find the equation mx plus c. This mx plus c is the line of, equation of prediction. So from the data set, from the data that we have, our algorithm will only help us to predict the equation. To predict the equation, it has to draw the regression line. Once you draw the regression line, then everything becomes simple, right? So how to do this? Again, you have to, okay, so let's say we divide it into train set and test set. Now we are going to run our model. So our first model is simple linear regression, and simple linear regression is in linear model of sklearn. So we'll say from sklearn dot linear model. Okay, import linear regression. You import linear regression. Okay, so now we are going to create an object. So I'll say regressor equal to linear regression. That's it. Our the object is ready. Now we need to train the model. So how do we train the model? Using fit, right? We've been talking about this, right? Fit will train the model. So we will say here regressor dot fit. Okay, and you pass the x value. So I'm going to say x train, right? And y train. I've hidden the test value for testing the, to testing the equation, how well the model has performed. Regressor.fit will draw your regression line and find out m value and c value. Okay, So how do you, after training the model, you can actually print the values here. So I'm going to say M, right? M is also called as coefficient. M
Yes.
or coefficient
Coefficient.
or your
Slope.
what is that?
Slope.
Slope, right? But
Yeah.
in machine learning language, we call it as coefficient. Okay. So here you can get regressor dot coef. This will give you the coefficient. Okay.
Mm.
And the constant term equal to
C.
regressor
C.
dot intercept.
Yes.
Okay. That is it. This is the whole purpose of drawing linear or working with linear regression. Isn't it simple? It is, right? With
Mm.
2 lines, we have performed our first model. Okay. So now when you run it, you get, okay. Okay. Let it run. Okay. It's taking time. It's performing linear regression. Okay. And finally, oops, Y contains NaN. Y contains NaN. Okay. Maybe, okay. What might have happened is we might have extra column here. So instead of -1, let me put as 1. It's possible, okay, that there could be an extra column and that last column may be the blank one. Okay, I'm just guessing. But why? Okay. Okay, so you see, this is the equation. So this is your
Mm.
coefficient. That means the equation it is giving us is y equal to m
M 7.5.
x plus c. Now, if I need to know, if you study for 10 hours, how many marks you will get? 10 into 5, 75 plus 20, almost 95% marks you'll get. Okay. Now, when I run it again, what happens? You will get different, very similar to this value, but you get different value. You won't get exact same value. So now you see 7.88 and it is 19. Very similar to this value, but different value. Why do you think different values? Because you see, when we're dividing into train set and test set here, when you're dividing into training set and test set, okay, we are saying 20, but that's all we are saying. We are not saying which columns to take. So maybe, you know, first time it might have taken first 80% rows. Okay. Second time it might have taken last 80%. Would have, so 30 means 6 columns from first 6 rows have been left. One time from bottom 6 rows might have been left. The next time you run from the middle 6 rows would have been left. So it can create multiple combinations of your training data. So when you run it, you will have a different answer. Okay, if you want it to take same set of values every time, which is not recommended when you put it in the production environment when you deploy it, but for learning training, you can do that. We have to use what is called as a random state. Okay, so random state means I'm saying that don't be random. Every time you take, and it can be any value, okay? You can say 0, 1, 10, 100. So I'm saying don't take random values. Whatever value, you know, associated with 100, you take it. So if I run with 100, okay, you might get some value here. So here it is 7.49, right? Now, if you run it again, now you'll get same values.
Same value.
Because we have fixed the random state. So it cannot take different set. It's every time it will take same set of rows. If you take same set of rows, you get same set of output here. So this is good to see. Okay. And if you put a random state 100 in your machine, when you do it, you'll also get same answer only because we are forcing it to take specific set of rows. Okay.
Yes.
So you get same answer here. Okay. So this is how you have created your algorithm. Great. Algorithm is created. We have found out X and, M and C value, right? Now, the last step, of course, apart from deployment, is how confident you are about the performance of this model. We have to measure the performance. So today I'm just going to give you the code, how to do it, and tomorrow we'll discuss about it, okay? So what we'll do now is, you say, okay, fine, regressor, you have learned, great. Now predict the value for me. Predict the value for me for y test, because I've hidden it, right? So regressor.predict, and you pass x test. So x test is the rows that we have hidden it from the algorithm, and this will be the predicted value for x test, and y test we have hidden it because that's the actual value. Okay, so what we need to do now is you have to compare. Okay, so I'll say result df. Now I'm going to compare how well this model has predicted. Okay, so I'm going to say pd.data frame. I'm going to create a data frame of what? So I'll create data frame of actual versus predicted, right? So I'll pass them as dictionaries here. So what is actual? Actual that we have hidden from this algorithm is y test, right? So this is y test. And now I'm going to say predicted. Predicted is from the model. Okay, so this is our y pred. Okay, now if you print the result df, so result df will have y test and the value which is predicted by our model. You see, actual value. So these are the rows. Okay, so see, when we put 100, first 6 rows are hidden for or taken for test data. 0, 1, 2, 3, 4, 5, right? This is the index number. Okay, now you see here. Okay, and this is y, by the way. So this is not from the df, this is from the y. It will always be 1 to 6 because we have dividing x and y separately, isn't it? Now you see here you have 46, which was y test, and the model is predicting 49.31 marks. 94, 92, 98. See, this is almost correct. This
Almost.
error is high here.
Sure.
Okay, here also little high, right? So this is how our model has predicted the different values. Okay, this is actual from the y test, and this is from your predicted value from the model. Okay, so okay, this is how we predict. Now, if you want to figure out how well it has performed, okay, we have difference metric. Okay, remember we discussed this some time back about mean squared error and standard deviation and things like that.
Yes.
Okay, similar concepts are there. We'll discuss it tomorrow. Okay, so this is the output. How do we analyze the output, right? So we will do the analysis of the output tomorrow, and also we'll start talking about the multiple linear regression tomorrow. Okay,
Yes.
we'll stop here for today.
Okay.